then describe how we do event processing, and how we do event description, and how we do event processing, and then how we take those events and distribute that event processing and distribute those across nodes and hardware. And we're going to talk also a very small amount about the open source implementation of the core of this, which is a project called Myrmas, where we've taken the kind of the heart of our product, not necessarily the distributed aspects of it, but the event processing aspects of that, and we've packaged it up in an open source application that we're getting ready to release here very shortly. And finally, because I've had a ton of questions about it, I'm going to talk about our use of SML as an embedded optimization language for Erlang. I should talk a little bit about what 10IO does, which is my company, to give you guys an overview of kind of why we're doing what we're doing. So this is the one-sentence marketing spiel for 10IO. This is what we like pitch to people as we're walking down the hall with them. So 10i keeps CIOs and their teams off the hot seat by transforming their data centers, cloud platforms, smart sensor arrays into autonomic computing infrastructures that are easier to operate, have fewer costly unscheduled failures. This is our business case for being. So, but what does that actually mean from an engineering standpoint? This sounds really great from a sales standpoint. You're talking to a CIO, he's like, yeah, I don't like being in front of my CEO saying, yeah, our infrastructure failed and we were down for 10 minutes and that cost us $30 million. And so that sounds great. But from an engineering standpoint, what does that actually mean? So what it means fundamentally is that we take existing known failure patterns and we combine that with operational data, and that data can come from places like log files, Andrix logs, Apache logs, collect D data, D-message, syslogs, Nagios outputs. It can come from almost any point in your operational infrastructure. We can take sensor telemetry streams, basically time series data, and we can take also like RESTful documents that have import to your system infrastructure. We take all of that, and we take these known patterns, and we combine them. We search, we apply those patterns to the data we're getting in real time so that we can take action. Now, in the very simplest case, and for many of our customers this is the case, those actions are simple alerts. They're emails or they are pages that go to an operational person and say, hey, do something. The best case is for the customers that are more advanced, that's us actually taking control of their network infrastructure and making a change to support continued operation. To give you a simplistic example, we could say that we have a data center. In this data center, we have a bunch of racks. On these racks are routers that serve the servers that are on the other side of that router that consist of the racks. And let's say that this router is starting to drop packets. And we start seeing CPU load and I/O load on those servers on the other side of that router start trailing off. And on this side of the router, the ones that are still exposed and still working properly, we see that load start to trail up. So recognizing that pattern, and in the simple case, saying to sending an email to an operation saying, hey, this is happening now, this rack is falling out of service, provision a new rack and do something about this. Or in the best case, we provision a new rack ourselves, we bring that rack online, and we deploy it, we test it, make sure it's good, and then once that's working, we take the old rack offline and then notify someone to say, hey, this needs to be maintained. So that's what we're doing. That focus on looking at this quantity of data, applying these known patterns, and then doing something about that. But what this means is that there are things that we don't do. So we don't do machine learning. We're not looking for unknown patterns in the data in real time. We're not trying to surface those patterns as the data passes through us. And I'll talk about one aspect we do want to do shortly. We don't do post-processing. We don't do batch querying. We don't do the forensic analysis of the data. We want to, let me re-articulate this. Our goal is to solve the problem either as it's happening or before it happens. And that's where we find a tremendous amount of value. The forensic analysis, figuring out why something failed, is very valuable as well. ton of companies doing that, coming up with those reasons. We want to take them and we want to do it as it's failing. We want to take proactive action such that the system doesn't actually end up failing. That's the goal. So on machine learning, one thing we'd love to do is look at the data, post-event, surface new patterns, and feed those back into our system. That's a little bit further off. So, given the nature of the data, the better title for this talk might be Complex Event Processing on Arbitrary Semi-Structured Data in Real Time. Another thing we're not doing NLP processing. We're not looking at arbitrary text documents to make any kind of decision. Like, all of the data that we are looking at is already structured in some way. It's log files that tend to be, we'll go into a little more detail, they tend to be structured in a certain way. So what do we do when we start seeing this data? First, we want to structure it into something that we can look at. Then we want to take it, we want to make it uniform. We want to turn it into something we can reason about, turn it into something we can cheaply and easily process, because we're doing this a ton. We're getting a quantity of data, we're doing this pattern matching. The more uniform the data is, the more we can do with it. And then we want to process it. So let's start with a log file. This is a very simple log file. It might come from an application. Let's say that we have an IP address and it's space separated and new line separated. We have an IP address, a timestamp, an error code. Let's say this is from an HTTP log, and the file that the user was trying to access. The straightforward, simple, automatic conversion to an arbitrary term that we can look at is really simple. We just do space separation and turn that line into a term. And do a little bit more so that we can take the floats and the integers and turn those into floats and integers so we can match in an appropriate way. And if we want to, we can add a little bit more description, or actually our customers can supply us with a little bit more description that will tell us that an IP address should look like a tuple of value, should be parsed on its own. And a timestamp should turn into an Erlang time tuple. And the rest can remain. But we actually don't want to do this a whole lot. We would actually rather do this, because we don't want to know about the data. Our system, and the one we're introducing here, has no insight on what the data means, has no insight on what individual terms signify. It only has, let me step from that, you give it insight in the patterns you write and the patterns you describe. And we want to maintain that. We want to have as little insight as possible on the actual data, so we can take data from a multitude of sources and simply match those against the patterns that you specify. So we can get data from a bunch of different places. You know, we take data from any place that is actually willing to give us data, and that comes into the pattern recognition system, comes into the boundaries of our system, gets parsed into this, and flows to the kind of locations where it's needed. There's a lot of infrastructure that goes in that. I'm actually not going to talk about a whole lot about that. I'm sticking on the pattern matching. But feel free to ask questions when we get towards the end. So we get data from say, Apache logs, from dmessage logs, and from arbitrary applications. We try to do something with that data. So let me step back just then. So we end up turning it into structured data. But it's not uniform. Like the Mozilla log has 6 or 7 fields, and some of them are integers, and some of them are tuples, and the dmessage log has other fields, and some of them are atoms, and some of them are strings, and some of them are other things, and the same with the final one. And we can process that, but there's a bunch of stuff we have to do. We want to turn that into something that's more consumable, that's more uniform. So what do? We actually turn these into triples, and if some of you have had access to kind of more traditional machine learning, it's very similar concept. We turn the entire term into a graph, and then we process that graph into a list of tuples of 3 values. And each tuple represents an element in that graph, represents a part of the term. The first is that we generate a unique ID for the entire graph, for the entire term. And this is a UUID that's only property is that it has a very high probability of being unique throughout the system. Not guaranteed, nothing in a distributed system is guaranteed, but a high probability. And an element ID that identifies the path through the graph for this particular element. So if you think about think about turning an Erlang term, and I'll go into some more detail in a second, but if you think about turning an Erlang term into a set of nodes, a set of vertices and edges, that path of the child for each vertices until you get to the scalar, the edge, is a unique representation for that element in that graph. So we give it an element ID, it's unique. And then we have the element value. For the scalar types, that's just the value itself. For the container types, for the lists and tuples, it's the quantity of elements that list or tuple contains. And that suddenly gives us a way for us to represent this term in a uniform manner. So I'm going to just really quickly go over how that element ID works. So again, if you think of the container types, the tuples and the lists as nodes in the graph, as vertices in your graph, the thing that matters is the node type and the position of the child within that node. So what we do for now is we give each level in the graph 16 bits as an identifier. The first 3 bits, and this is so trivially easy in Erlang, it's beautiful. The first 3 bits are the tag type, so we need to know if it's a tuple or a list or what kind of thing it is. And then the last 13 bits are position elements. So the thing that we found is that for most Erlang terms, that we're processing at least, they don't have a ton of depth. So you might get 2 levels of depth, or 3 levels of depth, or 4 levels of depth. They don't tend to go much deeper than that. So we can actually, because we use 16 bits for each level of depth, we can actually usually stay under 64 or 128 bits for each element ID. And that makes it basically, in most systems, a single instruction for us to do a comparison on that. It keeps it extremely cheap. At the downside of, we only have 13 bits for positional information. So if I remember correctly, and someone's going to comment on this if I didn't, that means that each tuple or list only has about 8,000 positions that it can actually represent. That works for us now. And it's very easy for us to change that in the future and be able to represent graphs of arbitrary depth at the cost of additional comparison, at the cost of a more expensive comparison. So basically, let me see where we are. Oh, so basically, we turn each of our tuples, and we're bringing this tuple representation up again, into a list of these, a set of these triples where we have the generated ID, the path, info, and type, and I didn't actually roll it out because it just ends up looking like numbers, and the value. So in this case, we have 4 elements, and the first element is a tuple, and the second element is a tuple with 3 values. The first element is a tuple with 4 values, an integer, and a string. So it ends up looking like tuple path information of 4 values, another tuple path information of 4 values, and the four values of the scalar information in the first one, another tuple of 3, the 3 values of the scalar information, and the scalar here. And of course, there's not space for it, but the last one. Now this has a bunch of unique properties. One of the nice, interesting properties is that we can move these around arbitrarily. There's an implicit, well, let me rephrase that. Ordering is not important because we're only matching on elements. And as we'll see once we get into a match description, it seriously affects how much actual data we end up having to move around. So let's step back a little bit and talk about patterns. So we've got a pattern description language, and this is a very simple kind of trivial description that I pulled out for example purposes. It's somewhat lispy with a Erlangish term definition. And in this case, what we are doing is we're identifying, you can see these little question marks are variables. We're saying that we want to see, first off, 3 values, 3 individual unique values that all have the same IP address, that are all 404 values, that have file information, and those files are different from each other. So we want to see a pattern that has 404 errors for the same IP for 3 distinct files. And then we want to see a 500 error. Why you want to do this is an open question, but it's good for illustrative purposes. So what do? Initially, we turn these same patterns, when we turn the elements of the pattern into the same triple structure that we used before with a little bit of additional information to identify variables. This is my favorite part of all this. This simply becomes a unification, a simple unification with our incoming data stream. And in fact, you can go to Norvik's book and look under unification, And you have like maybe 100 lines of code there that does this exact thing in a perhaps not as efficient a manner, but a similar manner to what it is that we do. So it takes the problem, decomposes it such that the solution, in the simple case, the non-distributed case, is actually very, very simple. And so we get a few other, and this is where I was going to go on further, we get a few other interesting bits from this approach. We get cheap filtering of that we only have to look at the data that matters to us, and we can get distributed, easy distribution, easy pulling apart of the actual unification. So let's look at the filtering first. So this is our value. We just saw it, and I've gone off the screen there. The same exact value, just to highlight what we need. And so if we go back up here, we can see that here we only care about 4 values. And in fact, we care about this one as a throwaway value. We care that this one is an explicit value, a realized value, and then we need to see these two. So we can take that, apply it to our triples, and initially, like on the scale, we can cut that other value down to just a subset. That these are the values we actually need to move around our system. And we can even further say that only values with a scalar need to move around our system for this particular pattern, need to move to where this particular pattern is consumed. And because these are scalar values, we can actually use filter techniques that are very, very, very cheap for us, like Bloom filter-based approach. And there are other approaches that we use that we can move part of the match, and we can subset the amount of actual difficult work we have to do at the consumption area, at the borders of our system, rather than consuming it in the unification, the expensive matching that we have to do to realize the pattern. And another thing to note is not only we can do this kind of filtering based on these kind of hard scalar values as well. So we end up with a larger amount of value, a larger amount of data, looking at it from the gross perspective, from the highest level perspective, but that data actually shrinks overall in the amount of data we actually have to move around our system. If you look at this pattern, I've lost my train of thought. There are at least five individual things that are going on. The first 3 things are matches that need to happen, and they actually need to happen in order. The first match needs to happen and be valid, the second match needs to happen and be valid, and the third match needs to happen and be valid. And then the fourth match needs to happen, but it doesn't have any dependencies at all on the things ahead of it. The whole pattern has a dependency on all those elements, but between these and the top 3, there's no dependencies at all. So we can actually pull those apart and do those in parallel. The same, and if depending on the nature of the system and whether this actually makes sense or not, we could actually do those top 4 in parallel and apply this as a third action on top of those matches. Now, depending on the nature of the data and a lot of other things, this may or may not make sense. And this very simple approach, we don't gain a lot by it, but this concept that it naturally falls out in a dependency-oriented way, which patterns need to happen before which other patterns, and which patterns can happen in parallel, and then fold up to the top-level patterns, that falls out in almost a thing you can get with like a simple topographic sort of your dependencies. And then splitting those dependencies off into different processes, and in Erlang, into different nodes, becomes a very cheap, very easy thing to do. We actually do quite a bit of that. That's one of the core values of the principle of our system, that we can do arbitrary matching, we can do arbitrary complex events on arbitrary large pieces of data, and the scaling factor for us is hardware. Now, of course, in the real world, there are intricacies that are involved in that actually being the case, but that's the principle we try to hold to. Doing this kind of breaking apart of the data, doing the compilation analysis on the events, and applying those inside of our system. So let's talk about Myrmas. This is the, and I fear that I've gone extremely quickly. This is the open source kernel of our system. The things that this does, it does the data flattening that we've talked about. It has to. It does the event description and recognition. Does the matching and unification. The things that it does do, there's no distribution involved in this. We're not releasing our whole system. We're just releasing the the core of our system, the pattern matching, the parsing, the distribution unification, as a library that you can make use of if you would like. And we of course, using it as the core of our world. And all of our distribution and mechanisms are built actually around that. So I said I would talk about SML, and specifically Milton, which is an SML implementation that we use as an extension language. In certain parts of our system that are critical path parts, it makes sense because it's a CPU-bound, it's a processing-bound approach to drop into a language that's a little bit more efficient in Erlang. And there are the traditional choices. There are C and C++, other languages if you want, but those are the more traditional ones. We actually don't want to use those. Actually, much less C++ than C. For the simple reason that while they give us speed, they don't give us a lot of protections. There's not a lot of controls in place. If we don't have to, we don't want to do our own manual memory management. We don't want something that's not going to tell us if we're doing like types incorrectly or something like that. And we'd much rather use a functional language than an imperative language in any case. So we went out and we explored the different solutions out there, and we ended up on SML, and again, particularly Milton, for a couple of different reasons. One of the big reasons for Milton is that it's only capable of using a single process. You can spin off threads and do concurrent things in Milton, but it multiplexes those off the one OS process, the one OS thread that it's capable of using. And for a lot of applications, this may be a downside. For us, this is actually a huge upside. Because we can use Erlang to control Milton, to kick off a new instance of the Milton interpreter when we need it, pin it to a process, and have total control of our embedded language, total control of the thread resources it's using from Erlang, and vastly simplifies the amount of control we get. The other very nice thing is less a feature of Milton, much more a feature of SML in general, is it's got a very nice type system, a Hindley-Milner type system. For those of you that are not familiar with it, you can think of it as perhaps Erlang having dialyzer built into the compiler. And you have to satisfy all the dialyzer warnings before it actually successfully compiles. So we get that removes a whole class of possible errors for us. And of course, the usual things with a functional language, it's garbage collected, has a really well thought out, consistent type system that removes a lot of problems for us at least. Trivial C integration. One of the nice things about Milton is integrating with C and therefore integrating with Erlang, because that's the method when you're doing a LinkedIn approach, is really just a matter of describing the function you're going to call and calling it. There's no wrappers you need to create in C. There's no hoops you have to go through. For integration with Erlang, it's a very nice thing. Another thing for us, although our optimizations tend to be small, Milton does whole program optimization, an extremely aggressive optimizing compiler that literally needs the source for everything it's going to compile. Even the libraries for itself does inlining and processing and all tons of optimizations to get the most performant compiled thing that it can get. So what that means is that we end up getting the speed of, at the very least, of OCaml, usually of C++, and sometimes of C, along with all these other benefits. So we get the advantage of these low-level native bits in Erlang without paying any of the costs, and getting actually a few benefits that wouldn't have occurred otherwise. So, like I said, I fear I've gone through this quickly, but I'm hoping there's going to be tons of questions. We're IO. We're 10 IO. We're working on autonomic networks, heterogeneous autonomic networks. I'm Eric B. Merritt. I'm the technical guy. We're a company of two people. My business partner's over there. Ron Singh, he's the business guy. We won't hold that against him too much because he is a lapsed engineer. And this is what we're working on, and I'm open to questions.
Was the choice between OCaml and Milton mostly for the performance, or of your 4 points?
So no, that's completely fine. So there's actually more than just OCaml and Milton. Once we kind of narrowed it down to an ML, it become those points. But C was obviously an original choice as the default, and Ada was actually in there too, which is not a bad language, and I'll actually digress and go into some reasons why that was. Between OCaml and ML, it really came down to us wanting the simplest thing that could approach, that could solve the problem. OCaml is very rich and very complex. If you look at the compiler sources, to me, at the very least, they're much more complex than ML. I feel confident that if I had a problem in Milton, which has not a huge community, I feel confident that I could go in and within a few days make reasonable that and solve my problem. I'm much less confident about that in OCaml. And it's not that the source is bad or anything, it's just a much more complex beast. And the other thing is that OCaml uses native threads, and I want control over that. And if I use OCaml, I want control over that from the Erlang side. I want this as an extension language, not as a whole language in itself. So I have much less control over that on the Erlang side than I have with ML. Once again, limiting it to a single process actually works very, very well for this use case. We can't get that with Erlang. With Erlang, we can't get that with OCaml. The other thing that kind of bothers me, and this is on a very abstract front, is that OCaml basically has a guild, a global lock around its library. So even though you have these multiple processes and they're taking up system resources, they're not actually concurrently processing once they pass into the OCaml library. And it just like, other than that, I actually like OCaml quite a bit. In one of our cases, one of our tests where we were doing Rete, the object system OCaml would have actually been a very nice feature. But in general, ML via Milton serves a much better approach. The other big contender one we did a little bit of preliminary research on was Ada, actually. Again, a very good compiler as part of the GCC infrastructure. It has a reasonable type system. The biggest problem for us with Ada was kind of twofold. First off, it's not really functional. And that's perfectly fine. You can do an imperative language, obviously. We're all comfortable in C and C++ and these things, and Ada fits along those models. But we prefer a functional language if possible. And the other thing is the type system is complex. And it has the feel of an ad hoc type system where the implementers of the language, and I have no idea if this is true, I'm giving you the sense that you get when using it, is that they would come up with rules for a type, and then work on some more types, and we need more rules, so add some rules onto that, and then over here we need more rules, so add some more rules to meet the problems as they arose. Whereas the Hindley-Milner type system that's used in OCaml and SML and Haskell, they came up with a rule and said, here's how types should act. And apply that rule across the board and consistently. And from an understanding what's going on perspective, that's actually a huge win, and at least in my mind. Other questions? Sure.
So I imagine that you have some stack for making your calls from Erlang to your small plugin. And so is there like a common transport format? Is that like
there basically is. So it ends up being something like so we actually kind of have we abused the NIF infrastructure a little bit. And we end up with something very like the traditional port driver, where we have the Erlang side and we have the ML side, and we're basically passing messages across those. And we got a very thin shim of C that kicks off the ML type and sets up a queue to move that data. And then everything else is done on the Erlang side and the ML side. Jet lag's a wonderful thing. But we're actually using the native Erlang format. We're not modifying anything. So we take control of we take ownership from Erlang, we pull it apart, we process it on the ML side. Again, Milton has extremely good C integration, so there's no overhead in doing that. Then we do what we need to do and send our messages to respond.
At the Milton end, is it just an ML data type that represents Erlang terms?
Well, it's an ML data type that represents C terms that represent Erlang terms, actually. But you rewrap it in such a way it doesn't feel like that, but that really is what it is. Like, C becomes the mutual mutually intelligible language between the two VMs. Well, not two VMs, because ML is not a VM, it's natively compiled, but between the two languages.